All right. So today we are going to continue talking about arithmetic for computers. We are going to focus on some IEEE standards to represent numbers in a 32-bit single precision format and a 64-bit double precision format. Before we get into the lecture material, I just want to point out a few things that are coming up um, Monday of next week. So Monday of next week is going to be our first exam, Monday, March 1st. We have our exam 1. So on Piazza, I will be posting some documents, some back exams, solutions, logistics, topics, and all that. On Piazza, I will be posting that sometime maybe today or tomorrow. So keep an eye out for a section that is going to be created under resources. It'll say exam 1, and it'll have some of the documents that you will need to get familiar with what to expect on Monday, March 1st. Keep an eye out on that. In the meanwhile, let's continue talking about arithmetic for computers, and this is our part 2 of the lectures that we have had. So we need a good way to represent real numbers, right? We know that our instructions are 32-bit. Our memory also has a certain fixed width. So keeping in context that there is going to be some size limitations, we are going to need a very consistent way or a standard, if you will, to represent numbers with fractions, numbers that are really, really small or really, really large. So for example, if you have numbers with fraction, if you have a limitation on number of bits, then obviously you cannot have absolutely an accurate way to represent them. The more bits you have associated with the fraction field, the closer you can get to the actual number, but there is going to be some representation error. We'll talk about how you can reduce that. So we need a way to represent fractions. We need a way to represent really, really small numbers. As you can see, this is 10 to the negative 12, 13, something like that. And very, very large numbers as well, right? Because you could need them in very practical situations such as computer graphics, scientific and engineering computation, and many other practical applications that need a representation of very, very small to very, very large numbers. So let's recall the scientific notation. And this is not for binary. Right now, we are sort of talking about things in the decimal world, right? So the world in which everything is straightforward, we are talking about decimal things, which is kind of obvious when you look at this particular number there, 10. So any number that you want to represent which is of decimal represent in decimal but using scientific notation, how do you do that? Well, you could have a positive number or a negative number. For that, you probably need something like this, -1 raised to the sign, either positive or negative. So that's one component to represent that number. The second one is significant, right? So that is essentially your value of the number, but you could also use that in the form of times 10 to the exponent, where you can change the value of the exponent to essentially move the decimal point around. So for example, if you have a negative exponent, that means that the significant needs to move that decimal point to the left. And if you have a greater than 0 exponent, that essentially means that you are to get to the actual number, you would take the decimal point in the significant and move it to the right by those many places. So this scientific notation has 3 components. There is a sign, there is an exponent, and there is a significant. Now, significant, you can call this in a couple of different names. So one way to call this is mantissa. And some part of the significand is also called the fraction. And we'll talk about when it is fraction and how is fraction different from significand in a little bit. So for example, this should be pretty easy. If you have a number in decimal number system such as 4564 decimal point 25, you can express that in scientific notation in the exact same value as 4 decimal point followed by all the digits to the right of the decimal point multiplied by 10 raised to the exponent, in this case 3. So if you have to go back to this, you are essentially taking exponent which is of a positive of value plus 3, and you are moving that 3 places to the right, giving you the value of the number itself. So the sign for this particular number is 0, indicating that it's a positive number. The exponent is 3, it's given right there. So let me highlight this guy in yellow here, and that's right there. And then in the significant field, we have the entire number. In this case, it is being represented in a normalized fashion. What does normalized fashion mean? Well, it simply means that you have one digit to the left, exactly one non-zero digit to the left of the decimal point. And then the decimal point, of course, and then followed by all the fraction, right? So you have one non-zero digit, decimal point, followed by a bunch of numbers representing the fraction part of the number. So significant, to call it normalized, I have to have exactly one non-zero digit to the left of the decimal point. And that's what we are going to call normalized scientific notation. And if the number does not follow that, we are going to call it denormalized notation. So far, things should be pretty obvious. But as we go from the decimal world to the binary world, the first thing that you would expect is this 10 to change to 2, right? That's going to happen. And then you're also going to change this significand to a fraction field, and we'll talk about why it is why we can do that in the binary world. As far as the sign is concerned, we still have positive values and negative values, so we are going to still need one bit to indicate the sign of the number. Now let's talk about whenever you're representing numbers, you worry about two things, right? One is how big or small can that number be if I want to represent it using bits, and how precisely I can represent it using those number of bits or those number of digits. Right now, again, we are in the decimal world for now. So let's talk about the range of numbers we can represent first. So suppose we have 2 digits for the exponent field, and then we have 2 digits for the significant field. If you have 2 digits to represent the exponent, then you can go all the way from negative 99 to positive 99 as far as exponent is concerned. Again, this is in decimal world, so negative 99 to positive 99 for the exponent. As far as the significand is concerned, we still have 2 digits, for example, so we can represent any number between, say, 0.1 all the way through 9.9. One is for the significand, one is for the exponent. Now, if you put these two on a number line and look at the range, you can see that the smallest number you can represent using 2 digits for exponent and 2 digits for significand is going to be, like I can color code this as negative 9.9 times 10 to the positive 99. That is going to give you the smallest number I can represent using 2 digits for exponent and 2 digits for significand. However, the highest number is going to be positive 9.9 multiplied by 10 raised to positive 99, right? So that's going to be the maximum. Now, once you have the least number you can represent and the maximum number you can represent, the difference between the two is essentially going to give you the range of numbers you can represent using these 2 digits for exponent, 2 digits for significand. Now clearly, if you wanted to increase the range or decrease the range, it is directly controlled by the number of digits you have for the exponent field, right? So for example, if you had 3 digits, then you could have gone from negative 999 all the way to positive 999, and your range would have gone from negative 9.9 to times 10 to the 999 to 10 to the 999. So that range of numbers that you can represent will go up and down depending on the exponent field, the number of digits in the exponent field. So clearly what we are trying to attach two things here. One is the range of the numbers and the other is the exponent field. And we are saying that if you want to play with the range, then you've got to kind of play with the number of digits in the exponent field. And the reason why we are talking about this in the decimal world is because things, when we translate things into the binary world, they are almost going to be similar to this, right? Even there we are going to have an exponent field, and even there the range is going to be a direct consequence of the number of bits in the exponent field. Now let's talk about the second thing you care about when representing numbers, which is the precision. How accurately can you represent those numbers? And just to continue with the same theme, we will say, all right, let's continue staying with the decimal world, and let's have 2 digits for the exponent and 2 digits for the significand. Now in this case, let us suppose that we are kind of on the positive side of this number line, and we are looking at two numbers that are adjacent to each other when very small and when very big, right? So if you are going to go all the way out to the right on this number line, what is going to be the difference between the two adjacent numbers? Well, that is simply going to be 0.1, which is the smallest change we can have in the significand, times 10 to the 99, because that is how big you are going to be changing, because the exponent has now to represent really large numbers, you would need the largest exponent. So the difference between two adjacent values over here is pretty large, in this case 10 to the 98. But if you look at this, look at the precision, or the difference between the two adjacent numbers when you are looking at very small numbers is going to be very small. In this case, the difference is going to be 0.1 times 10 to the negative 99, right? What that means is precision is going to be a changing quantity. If you are looking to represent small numbers, you have a very precise representation. But if you go for a very large numbers, then you may not have that same accuracy. In other words, precision is going to be varying over the real line. And also, the thing that we did earlier was to attach the range and exponent, because you change the number of digits in exponent, you change the range. Now to change precision, to improve it or not to improve it, that is going to be a direct consequence of more digits or less digits in the significand field. Because now, so I'm just going to first highlight this and kind of attach them, and then talk about what does that make sense, right? So suppose you have significant, you can represent that, say, let us suppose a case in which we are using 3 digits to represent significant. Well, in that case, what is going to be the smallest number and what is going to be the largest number? In that case, if you have 3 digits, you're going to have 0.01 all the way to 9.99, right? So no matter what that is, this is going to be 0.01 and this is going to be 0.01. The precision would have increased by a factor of 10. It still varies on the real line, but it has improved, right? So if you want more precision, then you increase the number of digits associated with the significand field. All right, so I hope that you see the two aspects of representing numbers, range and precision, and which the number of digits in which field controls the range and which field controls the precision. Now let's talk about overflow and underflow. And the reason why we need to talk about this is because after you represent numbers, you will be doing some arithmetic with them. You will be multiplying them, you will be adding them, you will be subtracting them. And no matter what you do, we are still going to have a limitation on the number of digits, whether it be the limitation for significant field or for the exponent field. We are still going to have a limitation on the range, right? Overflow and underflow are a direct consequence of the range of numbers you can represent. So if you are outside the range, then you say overflow has occurred, right? And we know that range is associated with the exponent field. So overflow and underflow are going to be related to the number of digits that are there in your exponent field. Let's go back over here and talk about what that looks like. So again, continuing the same theme, 2 digits for exponent, 2 digits for significant. So it gives you the smallest and the largest for exponent and significant in that case. Now, suppose you take two numbers represented using 2 digits for exponent and 2 digits for significant. You do some arithmetic with those two numbers. Your answer, your result could be in this safe region. In this case, we are looking at only the positive result, right? If you have a positive result, you could be inside this safe region over here where the smallest value is positive 0.1 times 10 to the negative 99, and the largest value is, again, we are using 2 digits for exponent, 2 digits for significant. The largest value that you can represent safely is 9.9 times 10 to the 99. But if your answer of that arithmetic falls above that or below this, between 0 and that, right, we are just looking at positive here, then you would call it positive overflow or positive underflow. In which case you are going to be having invalid or incorrect results for that arithmetic, which can be, avoided by either ignoring things or by, doing a exception handler program. So the designer needs to look at how they want to respond to those underflow or overflow conditions. But this could also happen on the negative side, right? Because once you do the arithmetic, your answer could be on the positive side or your answer could also be on the negative side. So now you're still doing like 2 digits exponent, 2 digits significant. Your answer could now be in the safe region, which is essentially limited by the smallest number you can represent or to the biggest number you can represent on the negative side. But if you are above that value, you would call that negative underflow. And if you are below that smallest value, you would call that negative overflow. Now, in your previous classes, you might have just heard the term overflow, which is the general term that we use for everything that goes beyond the range. But if you want to be specific, then you can say, all right, there is overflow and there is underflow. Overflow is something that you cross on the positive side, like on the higher side, and underflow is when you cross the boundary on the lower side. And again, in this case, you can have that for both the positive results and the negative result. And like I said, you don't want overflow to happen because that indicates incorrect results in the arithmetic, and the designer needs to decide how they want to respond to those kind of situations. Now, by the way, when I talk about overflow and underflow, do I have to worry about the operands or do I only have to worry about the results? That's a question to you guys. Yes, only the result, right? Because operands, well, I'm representing the operands using only those 2 digits in exponent and 2 digits in significant. So, I don't even need to worry about the operands because I have a limitation on how many digits I can use to represent them. Right? So operands is not the problem. The result of the arithmetic is what I need to worry about because that's not in my control. Depending on the numbers and the arithmetic chosen, that can get into the overflow scenario. All right. Now let's talk about scientific notation for the binary numbers, and we are going to be using floating point notation. Well, okay, so what is floating point notation? Wow, how is it different from its counterpart? Its counterpart being fixed point notation. So in fixed point notation, the name kind of gives it away, right? Fixed point. What point are you talking about? Well, if you're talking about decimal numbers, you're talking about decimal point. If you're talking about binary numbers, then you're talking about binary point. So if that point is fixed, then those are called fixed point numbers. So the location of that point, if that is not floating or changing, then you call it fixed. For example, if you have 5.25, that's it, then that's a fixed point number because that decimal point has been fixed. It's not changing. But now if you talk about 5.25 times 10 to the 2 or 10 to the 3, 10 to the negative 1, then you are kind of using the exponent field to keep that point floating, right? So by using this particular exponent field, you can keep changing the location of the binary or the decimal point, which is what we call the floating point notation. And we can move things to the right, we can move things to the left. When you have 10 to the positive numbers, you are moving the decimal point to the right. When you have 10 to the negative numbers, you are moving the decimal point to the left. And similarly, when you have 2 raised to exponent, if that exponent is positive, you are moving the binary point to the right. And when you have that exponent field to be negative, then you are moving that binary point to the left by those many places indicated by the exponent itself. All right, so let's come back. What are the three fields? Still a sign, still a significant, still an exponent. The only thing that changed, if you compare this to the scientific notation for decimal numbers, the only thing that changed is 2. Earlier it was 10. That's it. That's the only thing that changed. Okay, that's one thing. But it turns out you can actually manipulate the significant field as well to gain other things, to gain a bigger range. Let's take a look at how does it look like. So now we have 1 bit for sign. All right, I can't do anything about that. I just need 1 bit for sign. There is no give or take over there. There's no negotiation that can go on over there. Sign 1 bit, that's it. Now I have certain bits for the exponent field and certain number of other bits for the significant field. Now that is negotiable. Why? Because the number of bits I have in the exponent field control the range of the numbers I can represent, and the number of bits I have in the significant field control the precision of the numbers I can represent. So this is a question mark and this is a question mark, and it's kind of up to the user to figure out what suits the best for them. Do they want a bigger range or do they want a better precision, right? And it also depends on the actual application that they are using these numbers for. So bottom line, we need a standard. We cannot just keep this a question mark forever, right? Because we need something that is consistent, that is being agreed upon by everyone. So we need a standard, which is why we have floating point standards. We have 2 of them, which is defined by the IEEE standard 754, which was written up and agreed upon in 1985. So it's been a while. It's been around for a very long time. And there are 2 of them. There is a single precision 32-bit format, and there is a 64-bit, which we call a double precision format. And it was developed exactly for this same reason, the divergence of representation. Everybody was coming up with whatever they required, and they were saying, okay, I need 10 bits for my exponent. I need only 3 bits for my exponent field. The rest of them I can have for significant. Well, we cannot have that divergence because we need portability, right? We need to make sure that scientific code is portable from one computer to the other. Have standards changed over time? No, they have not. And the reason why they have not changed is because when you go from 32 bits to double precision 64 bits, the luxury is the improvement in the range, and more importantly, the improvement in the precision is so dramatic. Nobody wants to even talk about changing the standard. It's like I've got everything I need, so I'm not even going to worry about the number of bits. 32 bits, yeah, it is kind of tight, but when you go for 64 bits, then it's kind of like we are talking about 10 raised to positive 308. Nobody cares really about numbers bigger than that. Or the smallest number being 10 raised to negative 308. That's kind of the range you can represent using 64-bit double precision format. So really think about that. 10 raised to negative 308 to 10 raised to positive 308. That's kind of like a very, very big range. So, and the precision is also very, very good for 64-bit. So no change over time. All right, so it's now universally adopted. There are two representations, like I said, single precision and double precision. One is the 32-bit version, and the other is where you represent numbers using 64 bits or 2 words, right? So this is 1 word and this is 2 words. The word is 32-bit. So this range is kind of for this guy. All right. So the IEEE standard for 32-bit single precision numbers is 1 bit for sign, 8 bits for exponent, and 23 bits for fraction. Now, I hope you saw that we went from sign, exponent, significant to sign, exponent, fraction. How are we able to go from significant to fraction? Can we do that? Let's answer that by asking a different question. So I'm going to ask you guys, sure, I can do this. I'm going to ask you guys to pick a non-zero integer. Can you guys think of a non-zero integer? Keep it small so that I can, convert it to binary quickly. 17, all right. So if you think about 17 and treat it as unsigned integer, in this case, it's an integer already, but think of it as unsigned. So if 17, that is in decimal, and if we convert that to binary, what would that look like? Well, 17 is 16 plus 1, which means that I've got 16, no 8, no 4, no 2, and a 1. You guys agree with that? It is 1, 0, 0, 1, 3 zeros and a 1, right, for 17. Now, let us take a look at some other non-zero number. Pick it at random. Somebody else pick it maybe, or whoever wants to do it. Some other random 20, all right. 23, sure. So if it is 23 in decimal, what would it be when you convert it into binary? Well, for 23, I still need 16. I still need what? 4 plus 2 plus 1, right? So I would need 16, no 8, there is a 4, there is a 2, there is a 1. You guys agree with that? Now, think about this. What is the thing that you observe as a similarity between these two numbers? Can you guess something similar to this number and this number? Most significant bit is always 1. Yes. Most significant bit is a 1 here and a 1 here. Now here is the kicker. Can you guys think of any number which is non-zero, an unsigned number, where the most significant bit is not a 1? You can take any number. Is there any non-zero number with most significant bit other than 1? No. You are restricted. No, I'm not restricted, right? I'm not restricted with the number of bits because I'm treating them as unsigned. Roland says yes, unless you are restricted. I'm not restricted. I'm in the floating point world where I can move the binary point as I feel by manipulating the exponent field. So really this discussion essentially is for saying if you have numbers in which the number of bits required is not a limiting criteria, then the most significant bit needed is going to be a 1, no matter what that number is, except for 0 itself. You guys agree with that? That is why we can save 1 bit. Because if the most significant bit of any number is going to be a 1, then why am I using one of these fraction bits for that? Right? Why do I need to write 1 explicitly when for every number it is going to be a 1 unless the number itself is 0? So I can save 1 bit like that, right? Which is why we don't need to worry about the integer part of the significant. We only can express the fraction part. So we can make sure that the number is manipulated using the exponent field to come into the form of 1 point, whatever the fraction bits are, and use these to represent the fraction bits. Now let's come back to what each of these fields, what is the range. Now when you have an exponent that goes from 8 bits, what does that mean? That means that I can go as small as 8 zeros all the way to 8 ones, right? So that is going to be my bits that can go in the exponent field, 8 zeros all the way to 8 ones. Now if you want to translate that into decimal numbers just to get a sense of how wide that range is, all zeros indicate 0 and all ones indicate 255. Now if you remove the 0 for the 0 itself, and if you remove the 255 for say infinity, then you are kind of looking at 1 to 254 as the numbers other than 0 and infinity that you would need to express using this 32-bit number. We are going to have 0 and infinity and not a number using like some other special entries in the 32-bit format. So that's the reason why I'm not including 0 and infinity in this case. I have 1 all the way to 254. Now if you look at 1 to 254, that is a range of 254 numbers, but sometimes I may want my exponent to be negative and sometimes I may want my exponent to be positive. So if I split right in the middle, I will get 2 raised to negative 126 to 2 raised to positive 127. So that is essentially the range of numbers you can represent using a 32-bit format. And if you convert this 2 raised to negative 126 number to a decimal equivalent, like expressed as a power of 10, then that translates to 10 raised to negative 38. So any number that is as small as 10 raised to 38 to as big as 10 raised to positive 38 can be expressed using 32-bit format. And the reason was, this exponent field being 8 bits. So that's like going from all zeros to all ones. All zeros is 0 and all ones is 255. So that gives you a range of 256. You're going to need one sequence for 0, one sequence for infinity. So if you remove those two at the edges, you are left with 254. And out of those 254, if you want half of them, roughly half of them for negative exponents and half of them for positive exponents, you can have that particular range. And this is kind of the reason why exponent field is expressed in what we call XS 127 format. So let's take a look at some more details about this in a little bit. Now, if you have fraction field that is using 23 bits, that is equivalent to about 6 decimal digits. So that controls sort of the precision of the numbers you can represent using this 32-bit floating point standard. So our goal next will be, given a number, can you find out the 32-bit sequence? And given a 32-bit sequence, can you find out the number? So we'll do some examples to go back and forth. We talked about this. Now let's come to this. Now, so we said, all right, 1 bit for sign fixed, 8 bits for exponent fixed, 23 bits for fraction, right? Not significant, fraction. So the question over here is this, right? Why did significant change to fraction? And we kind of answered that. Significant is essentially integer part. Significant is integer, then the decimal point or binary point, depending on what you have, followed by the fraction. Now, if this guy is always going to be 1 for the binary case, if this guy is always going to be the 1, I can just use fraction. Why? I don't even need a significant field in which I have an integer. I can just talk about the fraction. So I have the fraction field listed, right? Binary is special. The one non-zero bit to the left of the binary point must be a 1. So if it has to be a 1, then let us keep it implicit. That way, even though you have 23 bits, you kind of have 24 bits because that most significant bit is kind of 1. So you're not even representing it, but you have it. So the form in the binary is 1, no matter what that is. In the decimal world, it would be 4.5 or whatever we looked at earlier. This is always going to be 1 point, a bunch of bits represented by x over here, base 2, multiplied by 2 raised to exponent. Exponent over here is indicated using y's. So any number, whether it be positive or negative, large or small, fraction or integer, you can represent using 32 bits using that scheme. Now let's talk about how do you go from significant to fraction and backwards. The fraction is just the bits to the right of the binary point, right? 1 is just assumed. So 1 plus fraction, 1 and fraction is significant. So that way, fraction always has to be between 0 and 1, and your most significant, the integer part, you have to use the exponent field to move the binary point such that you have this normalized representation, 1 dot something else. And then you use the fraction field to represent only that x. Now let's talk about normals versus denormals. And the whole idea is, can you represent the numbers using one binary point followed by the fraction bits, or that is not possible, right? So 1 followed by a binary point followed by a bunch of fraction bits, that is called normal scientific notation. So the significant is normalized to the form 1 binary point followed by all the bits. They go here, right? The fraction bits. The leading one of the significant is implicit. Why use 1 bit out of the 32 bits when we know that 1 bit is going to be always 1? So for example, if you have a half, 0.5, you can represent 0.5 as, it's a positive number, so positive, 1 point, a bunch of zeros, but if you can multiply that with 2 raised to negative 1, even though all your fraction bits are 0, because you have multiplied by 2 raised to negative 1, that is equivalent to moving this binary point left by 1 position. So that means it is really 0.1 in the base 2 times 2 raised to 0 if you use up that 2 raised to negative 1, which is 0.5. So what are we going to do? Are we going to represent half or 0.5 using this or this? The answer is, let us do this so that it is in the normalized fashion. 1 dot followed by a bunch of fraction bits. multiplied by 2 raised to the exponent. So we can keep using that exponent to keep the binary point floating. Only the fraction is included in the IEEE form, so we don't really need to write that particular one. Exponent is represented in the XS127 format, which means whatever 8-bit field you have for exponent is not the true exponent. You are going to manipulate it in order to cover positive exponents and negative exponents, both. So the exponent field that you have using 8 bits is actually the true exponent plus 127, which is called a XS127 format. So the value of the number can be computed as -1 raised to sign, which is very straightforward from before, followed by, instead of significant, now what we have is 1 plus fraction, multiplied by 2 raised to, instead of just exponent, you have exponent minus 127. Why? Because 2 exponent is actually exponent field minus 127. So once we start doing some examples, everything kind of fits in. So here we have an example where we have a number f, which is represented by a 32-bit floating point number. So it's a single precision format number represented in hex, right? So 0x followed by C2E480000. All right, fine. So let's convert it into binary first as a 32-bit number. So in binary, what does that look like? You have got 1 followed by an 8-bit exponent followed by 23-bit fraction. How did you go from here to here? Well, we expanded each hex digit using 4 bits. Something that you guys have been doing, many times in COCO or your other prerequisite classes. Expanding each hex digit into 4 bits. In this case, I can just take an example here for one of them. Maybe I can just do it for C. What is C? A, B, C, 10, 11, 12. 12 is what? 1, 1, 0, 0, right? So that's your 1, 1, 0, 0. And then you have 4 more bits here and then 4 more bits and so on. Now, those hex digits, once you expand them, each hex digit has 4, we know that there is a separation, right? We have the first bit for sign, the next 8 for exponent, and the last 23 for fraction. So we just color coded it. The first bit for sign, it is 1, so indicates a negative number. Right away we know it's a negative number. The next 8 are exponent. So let's try to find the exponent field so that we can evaluate the true exponent by adding 127 to it. So 1, 0, 0, 0, 0, 1, 0, 1 is 133. And when you subtract 127 from it, right, this is the exponent field, right? So what we have is the exponent field. If you want to find the true exponent, then you have to subtract 127 from it. That's what we are doing here. We took this particular 8 bits and we found the decimal value to be 133. Then we subtracted 127 from it because it was in the XS127 format. So to get into its normal format or your true exponent, you subtract 127 from it, you get 6. So that's your true exponent. We know it's a negative number. We know the true exponent is 6. And what about the significant? Well, significant comprises of 1 dot followed by all the bits in the fraction field. What do you have in the fraction field? You have all these bits in blue in the fraction field. So you take all of that and you plug it in over here. What doesn't change is the 1 up front, because that is always going to be in a normalized 1 dot followed by a bunch of bits format. Once you have that, you have the number. The number is -1 raised to sign. That's your negative 1. Significant binary point followed by all the 23 fraction bits, in this case, multiplied by 2 raised to the true exponent, which is 6 in this case. So what does that mean? Well, you can do a bunch of things here. One is, you can because you have 2 raised to 6, that is sort of like moving this particular binary number 1, 2, 3, 4, 5, 6 places and evaluating that, which is and evaluating the number there, right, which is going to be what is going to be negative 1110010, binary point 0100, all are zeros. So that is, I've essentially consumed this 2 raised to 6 when I did that multiplication. And then you can find the decimal value of this, which is what, negative, all of this will be 114 and this will be 0.25. Or you can find the value in binary of this and multiply it by 64. You can also do it that. So there are a few options that you have. So if you want to represent a number, so now we did an example where we took the 32-bit sequence and we found the value it was representing. Questions about this example? Can you repeat how you got the 133 for the true exponent? Yes. So 133 is not the true exponent. The true exponent is actually 6, right? So, oh, Rojan has answered that question. This is this guy. So if you take a look at this exponent, so here, when you say exponent, right? 8 bits, it is not the exponent directly, it is not the true exponent, it is actually related to the true exponent. Related to true exponent. So you take this guy, what is this? 1 4 zeros, 101. Well, 1 4 zeros, 101, that's like saying what? 101, the last 3 bits give me 5, and the 8th bit being 1 gives you what? 128. So that's your 133. All right, other questions, you guys? Okay, let's move on. Now, if there is normals, then there is also denormals, also called as subnormals. And there is a specific motivation why we use denormals. And the motivation is we need a way to represent really tiny numbers that are around 0. Which, in other words, I can go as low as 10 raised to negative 38, which is also kind of very close to 2 raised to negative 126 using the 32 bits. That's the smallest I can go. What if I needed 10 raised to 39? What if I needed 10 raised to 40? What if I needed 10 raised to 41? So numbers that are very tiny, tinier than this, I can use denormals to represent them. What is the change? The change is, let us give up on that 24th bit of that fraction field. So earlier we were having a 1 as our significant, right? The integer part of the significant. Now we are not going to normalize it, right? That's why we are calling it denormal or subnormal. So what we do is we give up on that bit, and now we are going to have sign, we are going to have 0 point all the bits in the fraction field, multiplied by 2 raised to 0. That's going to be called the not normalized or denormalized or the subnormalized field. So in this case, our significand is going to be very, very close to 0, in other words, between 0 and 1, and our fraction is going to be the same thing as significand because the integer part has become 0. Now, because we have lost one bit here, we our true exponent is now not going to be exponent minus 127, it is going to be exponent minus 126. What is going to be the number? Well, the number is going to be -1 raised to the sign, exactly the same way as before. Now, we don't need something to be fraction versus significant. They are both the same here, so we can just write significant. And our true exponent is going to be fixed, 2 raised to -126. One bit here, 23 bits for that, and then 8 bits for that. So 2 raised to -126, what is that? 8 zeros in this case. So denormals are used for very, very small numbers that are smaller than 10 raised to 38 or smaller than 2 raised to -126. And one of the ways you can identify them is if the 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, if the 8 bits in the exponent field are all zeros, then you know it's a denormalized number, which means it's a very, very small number that is close to 0. But for this to be holding true, our 23 bits in the fraction field have to be non-zero, because if they are the zeros here and if they are zeros here, then the value that we are representing is actual 0, absolute 0. So in order for us not to get confused, you have 8 zeros here and some non-zero 23 bits over here. That is what qualifies as a denormalized number. Right here. Right? A bunch of like 8 zeros in the 8 bits. That's what gives us the lowest exponent. In this case, 2 raised to -127. 6. Not 127 because we lost that one position. So that leads us into our example 2, which is going to be a denormalized number. Again, we are going to start with f, which is in hex 8068800. It's a 32-bit floating point number. Let us see what its value is. So first we convert this hex into binary. Once we do that, we got one bunch of zeros and then 23 bits for the fraction field. Notice 8 zeros. The moment you notice these as 8 zeros, you know that either the number is 0 or the number is denormalized. Next, you perform a check on these 23 bits. The moment you see that these are non-zero, you know it's a denormalized number. So the first bit is sign. We see that it is 1. We understand it's a negative number. Next, we look at the exponent field. Once we see 8 zeros in the exponent field, that means that our number is not a normal. It can either be 0 or it can be a denormal. Now we look at the significand in blue. The moment we see that the significant field, in this case the same as fraction field, is non-zero, we know that it is not absolute 0, the actual 0. So that means that we are dealing with a denormalized number which has a particular format. The format is 0 dot bunch of p's, the bits to represent the fraction part, times 2 raised to 0. In this case, we are going to need 2 raised to -126. So we have 0 point followed by a bunch of fraction fields, fraction bits. So copy over all of these guys to here. We already knew that it is a negative number by looking at the most significant bit. Then we have times 2 raised to -126. So what can you do with this? Well, you can say this equals negative of 2 raised to -1 plus 2 raised to -2 plus 2 raised to what? 3, 4, 5. 2 raised to -5 plus 2 raised to what? 5, 6, 7, 8. All of that multiplied by 2 raised to -126, whatever number you get, that is going to be your answer in this case, right? that's going to be your answer in decimal. So if you actually carry that out, you should get done this calculation before. It will come down to negative 9.2295 times 10 to the negative 39. And as you can see, it is a number that is smaller than 10 raised to negative 38. So if you can classify these based on looking at the binary sequence or the decimal value. So if you look at the decimal value smaller than 10 raised to negative 38 or 32-bit single precision format, you know that it's a denormal. Or there's a way to check the binary sequence itself. You have to see all zeros in the exponent field, and you have to see something non-zero in the fraction field. Questions about this example? Let's move on to another example. This is example number 3. We are converting a integer, in this case 9, to this IEEE 754 standard. How can we do that? Well, let's take a look. 9 is represented in binary as 1001. That's your first step. Second step, to normalize it. So what does that mean? Right now, the binary point is way over here. So if I want to move this 1, 2, and 3 positions to the left, then I can express this number in the normalized scientific notation as 1.001 times 2 to 2 raised to 3. So I've got 1 as my integer part of the significand. I don't need to express that explicitly. Just need the 0.01 bit, and then I also need the exponent. Here the true exponent is 3, right? True exponent is 3. In order for me to find the exponent field, which is kind of the 8-bit field here, I need to do true exponent added with 127, because it should be in excess 127 format. So that gives me 130. Using that 130, I'm going to translate that into a 8-bit sequence, and that will give me 100000010. So that's 130. So putting things together, I've got my sign bit over here, positive, right? It was positive, so that gives me positive there. Then I've got the exponent field right there, 8 bits. The last thing is the fraction, 23 bits. In this case, I only need 001 at the front, and then followed by 20 zeros. And if you want to convert that into hex so that you can just write it in a very compact manner, you can do that as well. Group in the form of 4 bits, and then group as 4s, and then you have 4110, bunch of zeros. So that's your is this normalized or not denormalized? Is this a normal or denormal? Normal, yes. And the way you know it's normal is because the exponent field is non-zero, right? So right away you can say that it is a normal. Let's see. All right, questions about this example? Things are okay? Now, since we have dealt with an integer over here, let us also try to deal with a real number. So let's do another example here. Let's see. Let's convert negative 6.75 base 10 to IEEE 754 single precision format. That's the example we'll do, right? So let's see. Let's start with the sign bit. What do you guys think the sign bit should be? Right, so Jeff says sign bit should be 1, and that's absolutely right. We are done with sign bit, no worries. How about 6? How should I represent 6? Well, that's simply going to be 1, 1, and 0. Brilliant. How about 0.75? 0.11, right. I need a half and I need a quarter. Now, if I combine the two, 6.75 can be represented as 110 binary point 11. And after that, there are a bunch of zeros. Is this normalized? Not yet, right. So what do I need to do? I need to move the binary point 2 places to the left. In other words, I need to write this as 1.10110000 bunch of zeros multiplied by 2 raised to 2 because I moved the thing 2 places to the left. Now this is in the normalized form. I don't need to explicitly worry about this guy because it's always going to be 1. And this guy is the true exponent, so I need to find the exponent field. So let's do the exponent field here. Exponent equals true exponent plus 127. In this case, it's going to be 2 plus 127 equals 129 in decimal, which equals 128. 1, 2, 3, 1, 2, 3, 129. So that gives me your 8-bit exponent field. Next, I think I'm ready to write the answer now, right? I've got the sign bit, which is 1. Then I've got 8 bits to represent my excess 127 exponent field. And then I've got all these guys. Let us highlight them in pink. And I've got 23 of them. 1, 0, 1, 1, 0, 0, 0, 23 of them. So I've got this one is 1, this one is 8, this one is 23. That's how you would represent negative 6.75 in 32-bit single precision format. Questions here? How do we do this with decimals that are, say, 6 or 7 digits long? It's just longer, right? So you would I hope when you say 6 or 7 digits, you're talking about like the like something like this, right? Like 9, 9, 6, 7, 5, something like that. Yeah, you would convert them into binary first. When you convert them into binary, you will have a pretty long value, but no matter what that is, you will have a 1 up front followed by a bunch of bits, right? And then you will have 2 raised to whatever. A pretty big number because you would have to move it way to the right to get the actual value to match up. So same procedure, except that you will have a, right now we are dealing with true exponents like 2 or 3, right? In that case, you might have a true exponent like 10 or 12. You see that? Next example, we have convert 2 raised to 10 raised to negative 40 to IEEE 754. So when you look at this number, do you think it's like a denormal or normal? Looks like pretty small, right? Denormal, because it is smaller than 10 raised to negative 38. So you know that you are going to have to do something that is for denormal. So it's too small. We can do normals. So you're going to have to pick the strategy of denormals. And that is going to be it. Now the question is, how do you go to this from this? Well, here is the answer. The number is obtained, you see this? The number is obtained by multiplying by 2 raised to negative 126. So if I want to find the significant field itself, so that I can find the 23 bits for significant, then I need to divide it by 2 raised to negative 126 to get that value. So what I'm going to do is go over here and start with my 2 raised to negative 40. Sorry, not 2 raised to 40, 2 times 10 raised to negative 40. And I'm going to divide that by 2 raised to negative 126 to get the significant, or the fraction in this case, because it's denormal. When I do that division, you will see that this evaluates to 0.0170 in decimal. 0.0170. If you wanted to express that, if you wanted to convert that to binary, you would get 2 raised to negative 6, 2 raised to negative 10, 2 raised to negative 12, 2 raised to negative 13, 2 raised to negative 15, 2 raised to negative 16, 2 raised to negative 21, 2 raised to negative 23. So if you add all of them up, you get 0.0170. In other words, what I did was I essentially converted this decimal value to binary using 23 bits. That is exactly how you get all of those. So you see this guy over here, 2 raised to negative 6, that is showing you a 1 in that particular location. 6 places after the decimal point. So that would be 1, 2, 3, 4, 5, and then 6. And then you have 1 for 10. Yeah, then this is for 12 and 13. You have this for 15 and 16. You have this for 21 and this for 23. So that's what is involved over here. That's how you get this particular 23-bit sequence, and then you multiply it with 2 raised to negative 126, because that's how you are expressing your denormalized number. Your exponent field, because it's denormal, bunch of zeros, 8 zeros. So when you put this together, you got the sign first, then you got 8 zeros to indicate that it is a denormal, and then you got a 23-bit sequence computed based on the number divided by 2 raised to negative 126 to give you the significant. And then you can obviously convert that into hex to represent it in a compact fashion. All right. Let's talk about some special cases. Infinities and not a numbers. How do you deal with that? Well, the bottom line is you have got 3 fields, right? There you have got sign field, you have got an exponent field, and you have got a fraction field. Now, depending on if the exponent field is all zeros or all ones, you can identify 0 or infinity. And depending on the fraction field, whether it is all zeros or non-zero, you can use that to identify a denormal versus maybe a 0 or an infinity. Right, so let's take a look at what are those special cases. If you have an exponent field in which you have all 8 ones, and if you have a fraction field with all 23 zeros, that is indicative of either plus infinity or minus infinity depending on the sign bit. But no matter what that is, you can use things in subsequent calculations, avoiding a need to check for overflow. So if something becomes infinity or negative infinity, you can continue using that in your calculations. Things don't stop once you have those numbers in the 32-bit format. Now, how about if all the 8 bits in the exponent field are all ones, and your fraction field, instead of all being zeros, it is non-zero. That is indicative of not a number, which often happens when you divide a 0 by 0. So it indicates illegal or undefined results. 8 bits in exponent have to be a 1. All 23 bits have to be non-zero, right? That means any one bit has to be non-zero. You can still continue to use it in subsequent calculations. How do you deal with arithmetic in floating point numbers? Well, addition and subtraction, the first thing that you need to do is equalize exponents. So let's suppose you have an example here where you have 1.6 multiplied by 10 raised to 10, and you're trying to add that to 2.3 times 10 to the negative 9. The first thing that you would do is equalize exponents. So you can do this number to that or that number to this. Let's just say that we are adjusting the first number. So let's say we have 10 raised to negative 9 here, and then 2.3 10. Once you do that, what do? Well, you just add the significants, right? You add that number to that number. What do you get? Well, you get 2.46 multiplied by 10 to the negative 9. And you normalize, which means that only one non-zero digit to the left of the decimal place. In this case, decimal, but when you are looking at binary, it would be the binary point. And then if you needed to round the significand of the sum, in this case 2.46, if you needed to round that, you would round that. How about associativity? So suppose you were doing addition of 3 numbers or subtraction of 3 numbers, how would you do it? A plus B plus C. Well, because you know that addition and subtraction, you have to be a little bit careful when you are doing associativity, right? Because it depends on whether you are adding them or not, so adding them or subtracting them. It also depends on whether the first addition or subtraction resulted in an overflow or not. So that is kind of subjective, the associativity. But in general, addition and subtraction can be performed correctly by first equalizing the exponents, next adding the significants, and then rounding off the significant of the sum. How about multiplication or division? Well, similar things, right? So suppose we have the same numbers, but let's say when we have negative 1.6 times 10 to the negative 10, and you wanted to multiply this with say 2.3 times 10 to the negative 9. What would you do? Well, you would add the exponents in this case, right, to get your 10 to the negative 19, and then you would multiply the significants and then normalize, which will give you say negative 1.6 multiplied by 2.3 gives you 3.68. In this case negative, because you have one of the significants is negative, and then you can normalize depending on the number of digits associated with the significant field. In other words, number of bits associated with the fraction field for the binary case. So you are able to deal with arithmetic in floating point numbers by treating exponents and significants kind of differently for different arithmetic operations. Now let's talk about the all the cases that we have gone over in this 754 number types. You have a table here in which all the way to the left you have the type of the number, whether it is normal or a 0 or a denormal or an infinity or a not a number. You have the sign bit, you have the exponent field, and you have the fraction field for each of those types. Now let's talk about the special cases first. 0. How do you identify 0 using 32 bits? Well, all of the 8 bits in exponent field have to be 0, and all the 23 bits in the fraction field have to be 0. How do you identify infinity? Well, all the 8 bits have to be a 1 in exponent field, and all the bits in the fraction field have to be a 0. Next, how do you deal with normals? Normals are the most often appeared, right? So in this case, you have an exponent field which goes from 1 to 254, like I talked about, at the very beginning of lecture today. But for the fraction field, it can be any bit pattern. Denormal. For denormal, things are a little bit different. You have all the 8 bits in the exponent field to be 0, and some non-zero bit pattern for the fraction field. For not a number, again a special case, all the bits in the exponent field are 1, and any bit pattern for the fraction field. And as you can see, all of these special cases are using a bunch of combinations, right? Whether the exponent field is all zeros or all ones, or none of those. Fraction field, all zeros or any bit pattern. Alright, so once we talk about that, now let's talk about the double precision format, but we are not actually going to go through examples over here, because only what has happened over here is now we are using two 32-bit words instead of one 32-bit word, right? So only the size has increased. So let's talk about the size here. Instead of using 8 bits for exponent, now we are using 11 bits for exponent. And instead of using 23 bits for fraction, we are using 20 bits of fraction from the first word and 32 bits of fraction from the second word, resulting in 52 bits for the fraction field. So 1, 11, and 52. And as you can see, the jump in the exponent field has been just 3 bits. But the jump in the fraction field or the significant field or related to the precision has been from 23 to 52, a dramatic uptick in the precision. But still the range has also increased because of the 3 additional bits in the exponent field. So let's talk about how the range has increased. Range with this 11 bits has become now 2 times 10 to the negative 308 to almost 2 times 10 to the positive 308. So that's a pretty high and small number, large and small number. So modest improvement in exponent, 3 more bits, but a huge improvement in the significant because of the 29 more bits. So much greater precision. Now, in terms of Mips instructions for floating point arithmetic, there are actually 32 floating point registers. 32 floating point registers that help with this. They are numbered $F0, $F1, $F2, $F3 all the way to $F29. Sorry, $F31. Those are all the registers, 32-bit registers that are used for single precision floating point registers. So those are for single precision arithmetic. The instructions for single precision arithmetic are add.s, multiply.s, division.s, and so on. The story for double precision is .d after the instruction itself, add and so on. And because it is now double precision, we use the same registers but as pairs for double precision. So F0 and F1 together make it a 164-bit register. Then F2 and F3 and so on. So only 16 double precision floating point. Alright, I'm going to stop here. I'm going to let you guys work on the activity today.